Welcome to Brain Vision.
All right, so what we have here is a fun little problem that tells us or illuminates to us how scales work. And what the scale is doing is that it's not measuring your actual mg vector, but rather it is measuring the strength of the normal force, um, because that's how much is pressing. So in this example, we're going to say that our weight is to three significant figures, 383 newtons, and then what I just said will make more sense when I draw a free body diagram. So, oops, I meant to draw that in a different color. But if this is u and you have a weight vector of mg pointing downward, again, what the scale is measuring is the normal force N and not mg, because when you are in an elevator that is either accelerating or decelerating, it's the ground, the bottom of the elevator, that's pressing up against you. So your normal force vector can actually change to get bigger or smaller because obviously your weight is not changing. And this is illuminated by the fact that the scale readings will differ. The scale readings will differ depending on whether you're in an elevator that's not accelerating or accelerating or decelerating. So what I meant to do is say that is your weight in general, but in part A, the scale is going to say that your weight is actually 725 newtons because we are in the portion where we are accelerating upward. So it's 725 newtons it's not your actual weight at that moment in time, but rather your normal force. So what I mean by that is that we need to apply Newton's second law. We have the mass times the acceleration, and at that moment in time, the normal force exceeds your weight, so it's going to be N minus W. So there's a little bit of algebraic gymnastics that I want to do, but isn't necessarily necessary. So we want to solve for the acceleration at that moment in time, and just to make things a little bit more clear, I'm going to substitute mass for your weight divided by the force of gravity, because W is equal to M times G. And again, just do a little gymnastics so that we can see where this formula is coming from. So if I factor out the G, the G just comes out in front, and then factor in the W's, then we see that the expression comes out to be G times this dimensionless quantity of N over W minus 1. So it's a play on 9.81 meters per second squared, modulated by this dimensionless factor, which we saw will be given by the reading of 725 divided by your true weight of 683, and then subtracting 1. Plug that into a calculator, and we see that the elevator was accelerating at 0.603 meters per square second. That's a 0. Okay, now in part B, we have a similar setup, but the reading is that you lost weight. You supposedly only weigh 595 newtons. So because this is lower than your true weight, this means that the elevator is actually decelerating. So we apply a very similar formalism, do the same thing. So I'll just quote the result that we found earlier, which is that acceleration is equal to the acceleration due to gravity times the dimensionless factor of N over W. So we plug in our numbers of 9.81 meters per square second, normal force of 595, 683 minus 1. Plug in the numbers, and we get negative 1.26 meters per square second, so slightly stronger acceleration than before. And then the negative sign is significant because it means that the acceleration is directed downward, whereas before we saw that we got a positive acceleration, so the acceleration is directed upwards, and that's the interpretation of the sign.